Okay, this is the solutions video for the Kinematics motion graphs worksheet. There are 20 problems on this worksheet. Here is 7 through 10, then we have up to 15, then we have up to 20. So let's see if we can bang it out in one video. Alright, number 1, let's go. Okay, so we have a constant non-zero acceleration. So it's saying that it is accelerating and that acceleration is not zero and it's constant. And we know if our acceleration is not zero, then our velocity is not constant because acceleration is changing velocity. And so if we are accelerating, then the velocity is not constant. So if we have a motion graph question, the first thing that we do is we ask what type of graph are we looking at? Is it a D versus T or a V versus T? Then the answer choices are D versus T graphs. And without even looking at the question, I see that it's a D versus T graph, and I know that the slope of a D versus T graph is velocity. Okay, and now it said in the problem that the object, what is the object? A car? A cart. That the cart is accelerating, so that means that the velocity is changing. And we just said that on a D versus T graph, the slope is velocity. And so if the velocity is changing, then the slope of the D versus T graph should be changing. And a changing slope looks like a curve. Now looking at my answer choices, the question says, what's the D versus T graph that shows this constant acceleration? And I can see that there are two graphs that are curved, either choice 1 or choice 3. But I can see that it's a distance graph, and you can't take distance back. Like if you look at choice 3, you start off at 0 distance, and then you start to increase your distance, and that's fine. But then the line comes back to 0 distance? You can't do that with distance. You can do it with displacement, but not distance. So it has to be choice 1. That also makes sense because let's take a look at what the slope is actually doing. At the beginning, we have a positive shallow slope, then in the middle we have a positive medium slope, and then at the end we have a positive steep slope. And if the slope is velocity, which it is, then that is a positive velocity, small positive velocity, so moving forward slowly. And we have a medium positive velocity, which would be moving forward like quicker. And then we have a large positive velocity, which would mean moving forward faster, which kind of goes with accelerating, which is what the description of the problem was. It said that you're accelerating, and so the velocity is increasing. So not only is the D versus T graph curved, but it's curved like this, so it's choice 1. Let's look at number 2. Okay, 2 through 4. 2 has nothing to do with motion graphing, but 3 does. So let's start off with 2 by writing the givens down. Starts from rest, accelerates at 1 meter per second squared for 10 seconds. Then, after accelerating for 10 seconds, then it says it goes at constant speed, which means the acceleration is 0 for 20 seconds. And 2 asks for the speed after the first 10 seconds. So we have VI, A, and T. We want VF. And then we have 10 meters per second as VF. By the way, it says it starts from rest. That's why I said VI is 0. If it starts from rest, VI is 0. If it comes to rest, VF is 0. So 3 wants a graph of the motion. So we have 2 different legs. We have in the first 10 seconds, there's acceleration. And then for the next 20 seconds, there's no acceleration. And then if we're talking about motion graphs, the very first thing you identify is what type of graph is it? And this is a speed versus time graph. So facts that I remember about speed versus time, I know that the slope of a speed versus time graph is V versus T, is acceleration. And then the area under the V versus T is displacement. And now we know that the V final at the end of the 10-second interval is 10 meters per second. So we start off at 0, and after 10 seconds, we wind up at 10 meters per second. So that would look like that as a straight line, because it's a constant acceleration, and the slope of v versus t is acceleration. Then it said for the next 20 seconds there was no acceleration, so that would mean that there's no slope on a v versus t graph. And then that is the rest of the graph, and then it only gives 20 additional seconds, so they actually don't need the 40-second mark. So you can use the given information from number 2 and just do d's vit plus 1/2 at squared. You wind up with 50 meters. But also, earlier I said that the area under the v versus t curve is displacement. So if we're talking about the first 10 seconds while it's accelerating, maybe I can take the area under this shape, this triangle right here, and see what that area is, and see if I get the same answer. That's a triangle, and so the displacement will be 1/2 base times height. And the base of that triangle is 10 seconds, and the height of that triangle is 10 meters per second. And when you multiply seconds times meters per second, you get meters. You should, because when you work it all out, you get the same answer, 50 meters. How about that? Next, number 5. Okay, number 5 talks about someone throwing a ball upwards into the air, and then it comes back down and catches it. Alright, so let's think about that motion. So when you throw something up into the air, it's upward, so its velocity is positive, but it's slowing down, so you have a decreasing positive velocity. Then once you hit the highest point at that instant in time, it is not moving, but only for an instant, not for any amount of time, but only for that instant, that snapshot in time. It has 0 velocity. Then it turns around and starts to fall downwards. Then when you're falling, the velocity is downwards, it's coming down towards the ground, so that's a negative velocity, and it's speeding up. Now let's also think about the acceleration. When it's rising, if you have an upward velocity but you're slowing down, your acceleration must be against the velocity. That means the acceleration is negative. Then when you're falling, you have a downward velocity that's a negative velocity, and you're speeding up, so the acceleration is acting with you. Well, if your velocity is negative and the acceleration is acting with you, then the acceleration is also negative. And then even at the highest point, the acceleration is not 0, because what happens at the highest point is that the velocity goes from pointing up to pointing down. If you go from an upward velocity to a downward velocity, suddenly it flips the direction from up to down. That must be a negative acceleration. In fact, the acceleration is constant the entire time. So let's think about what that would look like as a graph. So again, when it comes to graphs, the first thing you ask is, what kind of graph is it? These are velocity graphs that we're looking at, not displacement graphs. Now we'll look at this in 2 sections. We'll look at it as rising and also as falling. So for the rising, we have some positive velocity, like if you throw something into the air, as soon as it leaves your hand, it has some kind of upward positive velocity, but gravity takes over and it immediately starts to slow down. So that's the first portion. We have a positive velocity, immediately begin to slow down, and then once it hits the x-axis, that's the highest point, where for an instant in time, the speed is 0. But that is for an instant in time. It does not hang out up there. You don't throw something up into the air, it reaches the highest point, and then it sticks around to enjoy the view. No, it immediately turns around and starts to fall downwards. So we have a downward negative velocity and speeding up as it falls. And so the second portion there, the negative velocity is the falling piece, where it's negative, so it's pointing downwards, and it's speeding up. Now, notice the slope. Notice that slope is constant. I hope so, it should be. And it's a v versus t graph, so I know the slope of a v versus t graph is acceleration. And in this particular case, it's the acceleration due to gravity at negative 10 meters per second squared. But I'm getting ahead of myself. This is about motion graphing, not about free fall. But at any rate, the answer is choice 4. Let's move on. I said I would do these 20 problems in a 30-minute video. I am not doing well. I'm almost at 10 minutes, and I'm only 5 problems in. Let's go! Okay, for number 6, Here's my sketchy version of this displacement graph, but it wants to know what the total distance is. So again, if you have a graph, the first thing you do is identify the kind of graph you have. This is a d versus t graph, not a v versus t graph. It's also a displacement graph, which explains why the displacement can go from 8 meters at 6 seconds out to 16 and then come back. You can't do that with a distance graph. Speaking of distance, it actually wants to know how far did it go in the 10-second interval. Always read carefully there. Sometimes they give you like 10 seconds on the graph, but then you want to know like, oh, what was the distance in 6 seconds? You just have to read carefully. But this time they went the whole thing, so let's take a look. So if you want to get d from a d versus t graph, you really just have to read the graph. So what I mean by that is that in the first 4 seconds, after 4 seconds, we've gone out to 8 meters. Then it holds that position for the next 2 seconds. And then at 6 seconds, it starts to go out all the way to 16 meters right here. So that's 8, and then from 8, it goes to 16. So we have 8 meters in the first 4 seconds, plus another 8 meters to go out to 16. And then from 16, it comes back to 8 meters again. So the end displacement, I know that's not what it's asking for, just bear with me here. The displacement, remember, start to finish. And so that would go from 0 meters, and it goes out to 16, sure, but it winds up at 8 meters. So the displacement is positive 8 meters. But the distance, which is what you cover, is 8 meters to start, plus another 8 meters to get out to 16. Then if you're going back to 8, from 16 back to 8, you're still covering 8 more meters to do that. So in total, the distance is 24 meters. And so that winds up being choice 4. All right, number 7 is asking about the relationship between acceleration of an object and time when it's freely falling. So we know that from free fall, the acceleration due to gravity is negative 10 meters per second squared, and it's constant at that value if we ignore air resistance, which we usually do. So again, it's a motion graph, so we identify the graph. This is an acceleration versus time graph, which is unusual. We don't usually see those. But I just said the acceleration due to gravity is constant. So which one of these graphs shows an acceleration that's holding a constant value? That would be choice 4. To be fair, the acceleration is negative, and it doesn't say magnitude of acceleration, it just says acceleration. So really, it's none of the above. It should be choice 4 is your best choice, but that acceleration should actually be in the 4th quadrant because the acceleration is negative. But here's the, for freely falling, this just says falling. It doesn't say rising, it just says falling. So for a falling object, here's what the graphs would look like. But yeah, just to talk about this a little bit more, the acceleration is constant at negative 10 meters per second squared. For a v versus t graph, we know that the slope is acceleration, so the slope should be constant, and it is constant negative slope with a value of negative 10 meters per second squared, or meters per second. And then for the d versus t, it's going to be curved because it's accelerating with an increasing negative slope. So with a shallow negative slope to start and a steeper negative slope later, because we know that the slope of d versus t is velocity, and so we would have a small negative velocity to start and a large negative velocity later. All right, next. Number 8, which graphs represent the same motion? Classic. Well, to do these guys, and these guys seem confusing, but you have to remember one basic principle. The slope of a d versus t graph equals the velocity. So, alright, so the answer is choice 1, and I can tell you why. Choice 1 shows velocity with an increasing positive velocity. That's what that graph is doing. And again, the slope of d versus t is velocity. So if the velocity is positive and increasing, the slope of the d versus t graph should be positive and increasing in steepness, increasing in value. So that's choice 1. Choice 2 doesn't work because even though the d versus t graph has a constant slope and the velocity is constant, that velocity is negative. The d versus t graph has a positive slope. No good. Then on number 3 shows the velocity going from negative and getting smaller to positive and getting bigger. And so at the very least, the d versus t graph should be curving because the velocity is changing, so the slope of the d versus t should change, and that's not happening, so no dice. Then choice 4 is not good because it shows a constant velocity, so the slope of the d versus t should be constant, and it's not. It's curved. So the answer is choice 1. Okay, number 9. Here's our velocity versus time graph, and it wants to know displacement after 6 seconds. So again, identify the type of graph. It is a velocity graph. So in order to get displacement off a velocity graph, you can't just read the graph. It's not a displacement graph. It's a velocity graph. So if you want to get displacement from a velocity graph, you take the area under the curve. So you break it up into shapes. Also, careful reading. They only said the first 6 seconds. So if we break up the area underneath this plot, we find that we have a little skinny triangle and we have a big square. And so we need to find the areas of those two shapes. So for the first 2 seconds, I find the area of this triangle right here. That triangle. And the base is 2 seconds and the height is 10 meters per second. I'm reading those right off the graph axes. Here's 2 seconds right here, and here's 10 meters per second. So that's my base and my height. So I do 1/2 base times height, and I get 10 meters for that section right there. And for that shape, I go from 2 seconds to 6 seconds. So that's 4 seconds for a base, and then the height is also 10 meters per second. So base times height, 4 times 10 is 40 meters for that guy. And when you throw it all together, you wind up with 50 meters worth of displacement for the first 6 seconds. Next, number 10, and these are all d versus t graphs. Again, identify your graph, d versus t graphs. And then it says which one shows something accelerating uniformly. Just remember that uniformly means constant, but then when you hear the word constant, don't be like, oh yeah, it's constant speed. Wrong. It is accelerating. It's the acceleration itself that is constant. So read carefully. This object is accelerating. So we need a d versus t graph of an accelerating object. So yeah, if you're accelerating, your velocity is changing. We know that. We also know that velocity is the slope of d versus t. Well, if you're accelerating, then the slope of your d versus t is changing, which means that the graph is curved. Now, it actually, you could argue, it's like, now wait, what about choice 3? Doesn't that slope change? Doesn't it go from a positive slope to 0 slope? You'd be right about that. But it also says that the acceleration itself is constant. So the rate of change is constant. And so that curve has to go all the way through. Also, for choice 3, there's no curve happening. Like there's an instantaneous acceleration at the kink in the graph there. So yeah, no, it's not choice 3. It's choice 4. Next. Also, don't get confused. Don't be like, well, why isn't it choice 2? It would be choice 2 if it was a velocity graph. It's not. It's a d versus t graph, so it's choice 4. Let's go. Okay, so 11 and 12 are both based off of this graph. And again, first thing we do is identify the type of graph. It's a v versus t graph. All right, 11 wants to know the acceleration of the car at 5 seconds. Well, first of all, acceleration, we know acceleration is the slope of a v versus t graph. But the slope changes. At 4 seconds, the slope changes from having a positive slope to having no slope. And it said, what's the slope at 5 seconds? Well, there's 5 seconds, and so if we look at the slope at 5 seconds, the slope right there is actually 0, so it's not accelerating. So the acceleration at 5 seconds is 0 because the slope is 0. Next question. And number 12 wants to know what's the distance for the full 6 seconds. So that's the entire time shown, and we know that for a v versus t graph, the displacement is the area under the curve. So we're going to need to break that graph into shapes. I see a triangle and I see a rectangle. Those are my two shapes right there, that triangle for the first 4 seconds and the rectangle from 4 to 6 seconds. So the base is 4 seconds and then the height is 10 seconds. That's 40. When you multiply them, half that's 20. 20 meters for the first 4 seconds. But they wanted the whole time. They wanted all 6 seconds. And you throw it together, you got 20 meters and 20 meters, so altogether it went 40 meters. That would be choice 3. Just a note about distance and displacement. These are positive values, so that 40 meters is both the distance and the displacement. But if the area were under the time axis, if it were in the negative velocities, that would be a negative displacement. So I would be subtracting that. You don't see that very often. But yeah, distances, you just add up the magnitudes, add up the amounts. You don't care about positive and negative, but displacement, positive and negative, does matter because displacement is a vector. All right, next question. Okay, 13. So we have a bunch of graphs here. I see that they are all velocity graphs. And the question is asking, which graph represents velocity for an object thrown straight upward? So velocity versus time for something rising up into the air. Well, we know if it's rising up into the air, its direction is positive and it's slowing down. So that's a positive velocity and it's slowing down, which means it's a positive velocity and the values are getting smaller. So looking at my answer options, choice 1 shows a constant velocity. That's not going to work. Choice 2 shows a positive velocity getting smaller, but it shows that it's curved. So does choice 3. Choice 3 shows a curve. We know that the slope of velocity versus time, the slope of that graph, is acceleration. And if the actual velocity graph were curved, that would mean the acceleration is changing. We know that the acceleration due to gravity is constant, and so the slope of the actual slope of the v versus t graph should not change. The slope of the d versus t graph would change if you're accelerating, but this is a velocity graph, so the slope should not change. The answer is going to be choice 4, but let's take a look at that graph because it's an important graph for freefall. Alright, so this actually says, the question talks about something going upwards, but the graph actually represents the round trip. So that shows, that first portion there is when you throw it straight up into the air. So yeah, when you throw it with your hand speeds it up, right? But this is right after it leaves your hand. As soon as it leaves your hand, gravity takes over. And this is for a thrown object. You can shoot something with a gun, you could like bounce off a trampoline, I don't care, whatever. It's launched into the air. Then gravity takes over, and you have an upward positive velocity, but gravity acts downwards. So that's a positive velocity with a negative acceleration, so you slow down. Then once you hit the highest point, the speed is 0 for an instant in time, but the acceleration is not 0 at the highest point, because even though the speed is 0 there, the direction changes from upwards to downwards. So even at that instant, infinitesimal moment in time at the highest point, you are still accelerating because your direction changes. Then for the last portion, when you slip into the negative velocities, now you're falling downwards, so your direction is downwards, but you're speeding up. So that is an increasing value. Your speed is increasing, but your direction is now negative. And the entire time, notice that the slope is constant. The slope is acceleration. That acceleration is due to gravity. So the entire time, the acceleration is negative 10 meters per second squared. Okay, I keep taking breaks to explain things, but I have about 5 minutes to do the rest of the problem, so I think I'm kind of making my point. I'm going to see if I can be a little more efficient here. Okay, v versus t graph, and it's looking for how far, so I'm going to take the area under the curve. and for the first 3 seconds only. Take the area of that triangle, 12 meters. Next. Alright, 15 is pretty much same as 14, just different numbers. Speed versus time graph wants to know how far in the first 4 seconds only. Take the area under the curve. There's our graph. And we get 40 meters, choice 3. Next. 16 and 17 are based off of this graph. So for the both of the questions, 16 and 17, we're dealing with a v versus t graph. 16 wants the acceleration, which we know is the slope of the graph. So there's acceleration 1.25 meters per second squared. If you did delta v over t, you would get the same answer. 17 wants distance, which we know is area under the curve, but it says from 4 seconds to 8 seconds. And again, to be clear, we keep seeing speed graphs and the distance is the area under the curve. If this were a distance or displacement graph, you would simply read the graph. So we have from 4 to 6 seconds, which corresponds to a speed of 5 meters per second at 4 seconds and 10 meters per second at 8 seconds. Let's look at the shapes. Now this one's interesting because they're like stacked shapes. I have a rectangle on top of a triangle. For my rectangle, the base is 4 seconds, because it goes from 4 seconds to 8 seconds, and the height is 5 meters per second. And then for the triangle above it, the base is 4 seconds, and the height is 5, because it goes from 5 meters per second to 10 meters per second. And again, to be clear, if you're not kind of half following along and you look at this and you're like, rectangle, triangle, what the heck is he talking about? There's the rectangle, and there's the triangle. And again, notice that 17 talks about show all work, equations, substitution with units. Whenever you're showing work, you should be doing that, even if it's a simple equation like finding an area. Write the equation, substitute with units, and give units with your answer. Alright, 18 wants to know the average velocity from 6 seconds to 10 seconds. Again, this is a velocity graph, so you could really just read the graph. If you wanted to be fancy, you could do v equals d over t, find the area under the curve from 6 to 10 seconds, and then take that displacement over the time. You get the same answer. And honestly, the velocity hasn't changed in that time from 6 to 10 seconds. It starts at 15 meters per second, it ends at 15 meters per second. So the average velocity is 15 meters per second. I didn't even need to add them up and divide by 2. Real quick, if you did a d versus t, the base would be 4 seconds, the height would be 15. 15 by 4 is 60. Over a time of 4 seconds, 60 divided by 4 is 15 meters per second. You'll wind up with the same answer if you do v equals d over t. 19 wants the acceleration in the first 6 seconds, which we know is the slope of a v versus t graph. Take the slope. 2.5 meters per second squared. One more question and less than 2 minutes to do it. Let's go. And 20 wants to know what's the shaded area under the curve, what they shaded in that picture. They shaded the whole thing. We know that the area under the curve of a v versus t graph is distance or displacement. You could honestly say either. They would take either one. Just one final comment on number 20, D, distance or displacement. Probably should write out the word. Just one final comment on something they said. They said physical quantity. When they talk about physical quantity, they are not looking for a number. They're not looking for a characteristic of a slope like, oh, constant slope or positive, or they're looking for a physical variable like velocity, acceleration, distance, displacement, time. When they say physical quantity, that's the answer that they're looking for. So just so that you're aware of that. They do that with slopes all the time. They call it the physical significance of the slope, and what they're looking for is a variable answer, like the name of a variable, distance, displacement, time, acceleration, impulse, momentum, fill in the blank, force. But yeah, so that's what they're looking for. All right, that's all the 20 questions. My video is telling me I have less than a minute left, and so I have 30 seconds now, and so I'll leave you with that. Thanks, bye.